Ever wondered if a brilliant AI is actually, well, brilliant? Or if it's just really good at cheating?
Cheating. How do you mean?
Well, like a student who aces every test not because they get the lesson, but because maybe they memorized the pattern on the classroom wall behind the teacher.
Ah, I see. Yeah, that sounds a bit absurd, but you've actually hit on a really critical real-world challenge in deep learning.
Right. Models often learn these sneaky shortcuts instead of really understanding what they're looking at.
That's precisely it. Those shortcuts are what we call spurious correlations. And our mission today on the deep dive is really to unpack a pretty groundbreaking new approach that helps AI focus on the right things.
Leading to hopefully more reliable, more trustworthy decisions.
Exactly.
Yeah.
You shared an academic paper with us introducing this method called IFAM. We're going
Yeah.
to dig into the core ideas and explain why it feels like such a significant step forward.
Okay, great. So let's unpack this problem first. This idea of AI unintentionally cheating. Deep learning models, they're amazing pattern finders, right?
Yeah.
But sometimes the patterns they find aren't the ones we actually want them to learn.
Mm-hmm. That's the heart of this spurious correlation dilemma. It's when models latch on to contextual cues, like you said, the background in an image, instead of the actual properties of the object itself.
Okay, give us an example.
Well, the classic one is a model trained to recognize cows. If nearly all the training photos show cows on grass,
Which they probably do.
right, the model might learn that grass is a key feature of cow. So you showed a picture of a cow on a beach.
It gets confused, maybe thinks it's not a cow.
It might completely misclassify it
Yeah.
because that usual grassy context is gone. This reliance on the setting, not the cow's actual features, well, it severely hampers generalization.
Meaning it doesn't work well outside its training environment.
Exactly. It leads to failures in out-of-distribution or ODE settings, where those typical correlations just don't hold true anymore. The context changes, the model breaks, even if the object is perfectly clear.
So why is this such a big deal for us, the users? Especially now AI is getting into really high-stakes areas.
It connects directly to this crucial need for explainable AI, or XAI. We absolutely need to be able to assess whether the attended regions are appropriate for a model's decision.
We need to know why it made a choice, not just what choice it made.
Precisely. If an AI analyzing an X-ray is focusing on, say, a drainage tube instead of the actual lung tissue to diagnose pneumonia, well, you can't trust that diagnosis, can you?
Absolutely not. Which brings us to attempts to solve this. What about current solutions? Do they work?
Well, people have tried different things. One common approach is using post-hoc explainability tools, things like saliency maps.
Ah, yes, the heat maps showing where the AI looked.
Right. They're appealing because they give you a glimpse into the model's decision-making process without having to change the model's underlying structure. They show you which pixels or regions seem most important for decision.
Okay, I see. So they show us what lit up. But how do we know the model only used those lit up bits for its decision? Is there a chance it's still influenced by other things?
That is the core limitation. The paper points out these are just post hoc approximations. They don't actually guarantee faithfulness.
Faithfulness, meal.
Meaning they don't guarantee the model arrived at its decision solely based on that highlighted area. It's like seeing highlights in a textbook, but you don't know if the student actually ignored everything else. You're just seeing an after-the-fact justification.
Okay, so post hoc isn't a guarantee. What about methods that try to build attention into the model's process, like these part discovery methods? P-discoformer is one mentioned.
All right, these try to guide the model towards the right regions during processing by highlighting relevant object parts. But this is where the IFAM paper really makes its mark, highlighting a key flaw even in these integrated methods.
Ah, okay, this is the innovation point. What were these earlier integrated methods getting wrong?
They found two main issues. First, these methods often work with high-level feature representations. Because these features have a large receptive field, they inherently gather information from the whole image, not just the specific part you want.
So even if you try to focus it, the basic building blocks it uses already contain background information.
Exactly. You end up with unintended background dependence anyway. The model's internal view is already sort of contaminated by the context. It still sees too much.
It's leaky then.
Precisely. And the second issue is their use of soft attention masks. These masks aren't binary. They're not just on or off.
Meaning they assign some level of importance everywhere.
Right. They assign non-zero weights to all locations, even the ones they're trying to ignore. This allows further unintended information leakage. Even a tiny weight means that supposedly masked background info can still subtly influence the final decision.
So the takeaway is, even these more advanced integrated methods weren't strict enough. They couldn't fully capture the model's reasoning without letting background sneak in.
Correct. They end up with similar reliability problems as the post-hoc methods. They tried to guide attention, but the guidance wasn't absolute.
That really sounds like a fundamental problem. If the very way features are represented lets background leak in, you need a different approach. So this is where IFAM comes in. What's the core breakthrough?
The core breakthrough is IFAM's carefully designed two-stage architecture. It's built specifically to tackle this leakage problem head-on.
2 stages. Okay.
And the design ensures that the second stage can only pay attention to the selected image regions, guaranteeing that it cannot make use of any information outside the mask. That's the key phrase, a guarantee of faithfulness.
A guarantee. That's a strong word in AI. How do these 2 stages actually achieve that?
Okay, let's break it down. Stage 1 is the selector, they call it flausel. Its job is simply to identify the relevant image regions for the task.
How does it do that?
It actually leverages the p-discoformer part discovery method we mentioned earlier. But critically, its output isn't just a suggestion, it's a binary selection mask.
Binary meaning strictly 0 or 1, on or off.
Exactly. At 0, 1 in, every location is either fully in, 1, or fully out. No shades of gray, no soft leaky weights. It's a hard cut. It figures out the foreground parts and everything else is just gone from the mask's perspective.
And looking at the paper's examples, you really see that. For a cat, it doesn't just highlight the whole cat shape. It picks out, say, the face part, the ears part, distinct components.
Or for medical x-rays, maybe the lung region, the heart region, specific anatomical parts.
Okay, so stage 1 makes a strict binary selection. What happens in stage 2?
Stage 2 is the feature extractor, BRED. And this is where the most academically innovative step happens, what they call early masking.
Early masking.
Yes. Think about how other methods work. They might extract features from the whole image first, and then try to apply a mask or attention layer later on.
Right.
IFAM flips that entirely. It applies the binary mask from stage 1 directly to the input of the stage 2 feature extractor.
Wait, hold on. So it masks the image before stage 2 even starts processing it to extract features.
Precisely. That's the crucial architectural shift. The paper says, since the masking happens at the input level, the receptive field is determined by the mask.
So stage 2 literally cannot see anything outside the mask. There's no way for background information to leak into its feature extraction process.
None. It's like putting actual blinders on stage 2. It only receives the pixels selected by stage 1. For something like a vision transformer, they implement this cleverly by modulating the self-attention mechanism itself with that binary mask. Attention connections from or to any masked out part are forced to 0. It surgically removes any possible influence from the background at a fundamental level.
Wow. Okay, that does sound like a guarantee. It's designed for faithfulness from the ground up. So the big question, does it work? What are the quantifiable gains?
This is where it gets impressive. On tough out-of-distribution datasets, the ones designed to trick models with spurious correlations, IFAM significantly improves results.
Like which ones?
On Metashift, which tests context shifts, it boosted the worst group accuracy, that's how well it performs, on the hardest subgroup, from 81% up to nearly 89%. It's a big jump.
Okay, 81 to 88.6. That's substantial.
And on Waterbird, another Trickio dataset, accuracy went from 94% up to 97%. The paper notes this is effectively halving the error on these really challenging benchmarks.
Halving the error. Okay, that's a serious improvement. It shows it's much more robust when the context changes unexpectedly.
Definitely. And it also performed well on things like the ImageNet 9 Backgrounds Challenge, which explicitly measures how much a model relies on background cues.
So the core design is powerful, but the paper also mentions some extra interventions, ways to make it even more robust.
That's right. The two-stage design also makes it amenable to some clever test time interventions. For data sets where spurious correlations are really strong, they can use a leave one out or LOO evaluation.
A leave one out.
Yeah. During inference, if the model identifies multiple parts, it can try classifying the image based on subsets of those parts, essentially checking if any single part is unduly influencing the decision in a spurious way.
Okay. And the other one?
The other is low confidence token removal. Sometimes an object from the background might look a little bit like a foreground part. This technique removes input tokens whose internal representations are too far away from the learned prototypes. the ideal representations of the target object parts.
So it cleans things up even further, making sure only high-confidence, relevant parts contribute.
Exactly. It prunes away potentially distracting elements that might have slipped through stage 1 or just look ambiguous.
And those visual examples from Waterbird really show this. You see the bird on its normal background, then the bird put onto like a bridge background. And IFAM, especially with that token removal, just cleanly isolates the bird parts. It completely ignores the confusing bridge. It's got tunnel vision in a good way.
And think about the medical applications, like the SIM-ACR dataset for detecting collapsed lungs, pneumothorax, from X-rays.
A critical use case.
Right. The model learns to find anatomical parts like lungs and the heart. IFAM helps prevent it from relying on spurious things often seen in chest X-rays, like drainage tubes, which might correlate with the condition but aren't the condition itself. The actual signs are often elsewhere. IFAM focuses on the relevant anatomy.
And combining these interventions helps.
Yes, the paper shows that using both LOO and token removal gives notable gains, improving performance by over 4 and 3 points on Metashift and SIM-ACRs respectively. So the core design is strong, and these interventions add another layer of robustness.
That really underscores the value. And they back this up with ablation studies, right? Taking pieces out to see what breaks.
Absolutely crucial for validating the design. When they removed the second stage, essentially crippling the core IFAM architecture, they saw the steepest accuracy drop on those robustness metrics.
Which proves that the two-stage design isn't just fancy, it's essential for the performance gains.
Precisely. It confirms that architecture is the heart of the innovation.
What about the binary mask? Did they test that against the leaky soft masks?
They did, and using soft masks instead of IFAM's strict binary ones caused performance to significantly reduce in out-of-distribution settings.
So letting any background information leak through, even a little, really does compromise robustness, direct validation.
It validates that core design choice. Faithfulness requires that hard boundary. They also found that properly fine-tuning just the second stage helps too, preventing it from overfitting to any subtle correlations within the selected parts.
Okay, this sounds really powerful. What about practicality? Is it super slow?
Actually, the speed seemed quite reasonable. Training on standard datasets like CUB or Waterbirds took about 3 hours on 8 high-end GPUs. Inference was around 43 images per second for a standard input size.
So it's sophisticated but not computationally prohibitive for many applications.
Right. And they even suggest future work could speed it up further by taking advantage of the fact that the input to the second stage is sparse. It only contains the selected parts. So there's room for more optimization.
Okay, let's recap. We've seen how AI models can easily get fooled by spurious correlations, basically learning to cheat by looking at the background or context.
And traditional explainability methods like saliency maps give hints, but no real guarantee of faithfulness. They show what lit up, not why.
Even early attempts at integrated attention suffered from information leakage through high-level features and soft masks.
Right. But IFAM introduces this innovative two-stage architecture with strict binary masks and, crucially, early masking.
Applying the mask before the second stage extracts features,
Which forces the model to focus with surgical precision only on the selected relevant parts, no leakage.
and the results are impressive. Significantly better robustness, having the error on tough ODE datasets with potential for even more refinement through interventions.
It's a fundamental shift towards designing AI for verifiable attention and trustworthiness.
So the final thought then, as AI gets deeper into critical areas like medicine or autonomous driving, how much more confidence can we have if we can actually guarantee what the AI is looking at and why it's making its decisions?
It's a huge step. And maybe what new things become possible when AI can no longer rely on those sneaky background shortcuts, but has to truly understand the core information we give it. That feels like the path to more genuinely intelligent systems.